Okay, Assalamualaikum and hi. Okay, so this is the continuations from the previous part. Okay, from the exercise number 1. Okay, actually I have answered the question for A. Alright, which I have constructed the table. Okay, so I do it again lah. So we have species here. Alright, and then the second column is the initial. Alright, and the third one is change, and the fourth one is the living. Okay, so we have a species of A, B, and C. Alright, and this is in terms of the flow. It should be in F. Alright, FA naught. This one is FB naught, and this one is FC naught. Okay, and the change will be negative FA naught X, and we have a B here which is minus 2 over 3 FA naught X and 1 over 3, okay, this product formations of FA naught X. Okay, so the living one you have to make it as a concentration. Okay, so from here we have a CA is equals to, okay, living is the change initial plus the change. Okay, FA naught 1 minus X. Okay, so this is a variable volume, so you should include 1 plus epsilon X. Okay, so from here this you can replace it with the CA naught. Alright, so for the B, CB is equals to FB naught minus with the 2 over 3 FA naught X over with the V naught 1 plus epsilon X. Okay, so this one you can put it as a FA naught. Okay, remember theta B is equals to FB naught over with the FA naught. Alright, so FB naught is defined as theta B times with the FA naught. Okay, so this one replace with theta B FA naught. Alright, so CB is equals to what do you call it, FA naught, right, theta B minus with the 2 over 3 X. Okay, so this FA naught you already put it in the left side here in the outer side. Alright, so and then we have a V naught 1 plus epsilon X. Okay, so this one becoming CA naught. Right, so for the CC is equals to we have a FC naught plus with the 1 over 3 FA naught X. Okay, so again this one we can replace also, okay, with the theta, which is the FC naught is equal to theta CFA naught. Alright, so this one is divided with the V naught 1 plus epsilon X. Okay, sorry. So from here just replace it, theta CFA naught, alright, plus with the 1 over 3 FA naught times with the X, or with V naught 1 plus epsilon X. Okay, so this FA naught you can put it in outer side, which is this is FA naught. Okay, so this one we can replace it with CA naught. Okay, so this will be the whole value for the table. Okay, so this one because there's not enough space, so I have to write here. Okay. Okay, for the next one, the B question is to determine the concentration of C. Okay, so what is the concentration of C at conversions of 85% of A? Okay, so you have to get the CC. Alright, so recall what is the equation for the CC. CC is equals to FC, right, over with the volumetric flow rate is equals to, right, so it should be theta C plus with the 1 over 3 FA naught X, okay, divided by V naught 1 plus EX. Okay, actually we have this term, but since it is in term isothermal and constant pressure, so we can omit this one. Okay, so this one also 0 because FC0 at T0 should be equals to 0. Alright, so what left is 1 over 3 Fn0 x, okay, V0 times with 1 plus epsilon x. Okay, so from here you don't have the informations of the Fn0, alright, and V0. Okay, this one we can replace it with Cn0. Okay, so 1 over 3 Cn0 x over with the 1 plus epsilon x. Okay, so from here there's some information that is not available from the question, which is the Cn0 here and also the epsilon. Alright, so you need to get the value of the Cn0 by using the ideal gas equation. Okay, which is we have a PV is equal to nRT. Okay, so C is equal to N over V is equal to P over RT. Alright, so how do you get the Cn0? Okay, so from here, okay, this is for Cn0. Okay, is equals to Yn0 times P over RT. Okay, so how we get this one? Okay, remember Yn0 is equals to Ca0 over with the CTO. Okay, so this is actually is TO for total one. Alright, so CT0 is equals to, so CT0 is equals to CA0 over with YA0. Alright, so if you want to put here, alright, YA0 akan naik atas ke sini lah. Alright, and then remain the CA0 here. Okay, so the composition of YA0 given is 30%, which is 0.3. And then the pressure in terms of 70, okay, atm, and then you need to divide it with the correct gas constant with the using the suitable unit, which is in terms of atm and also Kelvin. So we have this 250 plus 273. Okay, make sure when you do when you want to answer the questions from the assignment ke test ke, make sure you write down the full unit here. Okay, this one I just simplify it, but the space is I have a constraint on the space here. Okay, susah nak tulis, so I shortcut lah. So make sure the unit must be completely written down. Okay, so you will have the answer as 0.1189 mole over decimeter cube. Okay, so this would be the value for Cn0. Next, what you need to do is you need to get the value of epsilon. So remember, epsilon is equals to Yn0 times with the del. Okay, so the del is according to the stoichiometric equation, which is 1 over 3 minus with 2 over 3 minus 3 over 3. Then the answer is minus 4 over 3. Okay, so just put it the value that you obtain for Yn0 and del, okay, which is 0.3, okay, times with the minus 4 over 3. Okay, the value would be negative 0.4. Okay, so just put it in this what do you call it, in this equations, all the value that you obtain. Okay, so the x would be 0.85 lah. Okay, so at the end the answer would be the concentration of this C compound is 0.051 mole over decimeter cube. Okay, so that's the answer. Okay, let's move to another question. Okay, so a mixture of 28% SO2 and 72% air is charged to a flow reactor in which SO2 is oxidized. Okay, so this is the equation. We have a 2A plus B equals to 2C. Set up a stoichiometric table and find the final concentration for all components when the total pressure is 1485 kPa, and the temperature is constant at 227 degrees Celsius at 75% conversion. Okay, so this is the total pressure, means that you need to, there is a variable volume here. Okay, so the first thing you have to do is you need to identify whether this is a flow or a batch. Okay, so it's already stated here it's a flow, alright, and this is a gas system. Okay, so the first thing you have to do is to set up a stoichiometric table. Okay, so we have a 2SO2 plus with the O2 equals to 2SO3. Okay, so you can write as 2A plus B is equal to 2C. I don't know what happened to my voice today. Okay, and then A plus with the half B is equals to C. Okay, so construct the stoichiometric table. We have a species here, alright, and then we have a inlet ataupun kita panggil initial dia, and we have a change here, and we have a leaving here. Okay, so from here we have a SO2, we have a O2, SO2, and we have a inlet there. Alright, so we just be denote as A, labelkan B, C, and I here. Okay, so the initial would be FA0, FB0, FC0, and also FI. Okay, inilah inlet dia. Okay, so this one we have a negative FA0x. This one is minus 1 over 2 FA0x, and also FA0x. Okay, should be positive. Remember, inert, there is no reaction occurs for the inert. Okay, so this would be blank je lah. Okay, tapi kalau nak simple juga, you boleh define juga here. Teruskan, which is theta B FA0. Alright, this one is theta C FA0, and this one is theta I FA0. Okay, sebab dia ada initial value for inert. Okay, so from here, leaving is the initial plus the change. FA, okay, is equals to FA0 1 minus x. Okay, and then FB is equals to theta B FA0, okay, minus with the FA0x. Okay, ataupun you boleh buat F B is equals to, you simplifikan the FA0 theta B minus dx. Okay, then we have a FC here, which is theta C FA0, okay, plus with the FA0x. Okay, so here it should be FA0 theta C plus with the x. So for inert, okay, for the Fi is equals to theta I FA0, itu sahaja. Okay, we don't have direction here. Okay, so from here you need to find the final concentration for all components. Okay, so dia nak what is CA, what is CB, and what is CC, and what is CI. Okay, so daripada situ, this F ni you kena convert as a concentration. Okay, for example, we have for A, so CA is equal to FA over with volumetric flow rate, which is equal to FA0 1 minus x over with the V0 1 plus epsilon x. Okay, so this one would be CA0. So kita ada CA is equal to this equation. Alright, so here we don't have the value of CA0. Okay, you need to calculate it to find it, and also the epsilon. Okay, so CA0 is equals to YA0 P over RT. Okay, this one I already explained you previously how we get this CA0 and YA0 into the ideal equation, ideal gas equation. Okay, so you just plug in, which is this is should be 0.28, right, times with the 1985, okay, over with the 8.314 times with the 500. Okay, don't forget to convert into the Kelvin, the temperature. Okay, so you will have CNO is equal to 0.1 mole over decimeter cube. Okay, and the YA naught, okay, I have to write here. All right, the epsilon is equal to YA naught here, del. So YA naught is just now is 0. Berapa tadi? 0.28, sorry, 0.28. Okay, times with the del. Okay, daripada ni lah, which is I tak nampak pula ni. Okay, which is 1, okay, minus 1 over 2 minus with 1. Okay, so the answer should be minus 0.14 here. Okay, so you just put it all the value here, and you will be able to get 0.028 mole over decimeter cube. Okay, so we proceed to how to get the value for the oxygen, which is the CB. Okay, so CB is equals to FB over volumetric flow rate is equals to FA naught, alright, times with the theta B, okay, minus 1 over 2x, okay, over with the V naught 1 plus epsilon x. Okay, so this one we can replace with CA naught. Okay, so what you need to do first, you have to get what is theta B. Okay, so what is theta B? Theta B is about YB naught over with YA naught. Okay, remember that I told you before, theta I can be in term of F, can be in term of C, alright, can be in term of what do you call it, N. Okay, it's depending on which one you want to calculate. Okay, for example, Y naught and YA naught. Okay, so from here oxygen, but the question only given the percentage of the air. Okay, so you need to know what is the mole fraction of oxygen in the air, which is around 21%. So 0.21% times with the 0.72 divided by YA naught, the one that you calculate, that one being apa, what do you call it, the value is given in the in the question, which is 0.28. Okay, so you will have the value of 0.54. Okay, so you just put it the value here for theta B and epsilon, alright, and the answer of the CB is 0.0184 mole over decimeter cube. Okay, so for C, okay, this is for the product, is equal to FC over volumetric flow rate is equals to FA naught x or with V naught 1 plus epsilon x is equal to CA naught x. Alright, so you can replace it with CA naught 1 plus epsilon x. Okay, so from here it's just a direct calculation, because you already cancel the theta C, because theta C is equal to FC naught over FA naught. We don't have FC at T0. Okay, so this should be 0. You just plug in the value and you will get 0.084 mole over decimeter cube. Okay, so for inert gas, we have CI is equal to FI over with the volumetric flow rate is equals to Fi naught, okay, over with the V naught 1 plus epsilon x. Okay, so this one is equals to theta I Fa naught, alright, over with the V naught 1 plus epsilon x. Okay, sebab kita tak ada plus D over A ke I over A ke, sebab dia tak ada reaction. Okay, this is the initial one. Okay, so this one you can what do you call it, simplify as theta I Ca naught 1 plus epsilon x. Okay, so you don't have the value of theta I, you need to calculate it. So theta I, okay, so we assume that the inert is the nitrogen. The fraction of the nitrogen, okay, is around 78% in the air. Okay, so means that 0.78 times with the mole fraction of the air, 0.72 divided with 0.28. Okay, so the value would be 2. Okay, so you just replace 2 here and get the value of CN0 and epsilon that you have calculated before this, and the answer would be 0.223 mole over centimeter cube. Okay, excuse for my voice. I don't know what happened to my voice today. It's kind of husky. Okay, so we proceed to exercise number 3. Okay, hopefully you are catching up, following up with my lecture. Okay, so we have a 2a plus b equals to 2c, and it's carried out isothermally and isobarically in a CSTR. Okay, so the reaction is first order in B and first order in A. Okay, so means that it should be negative R A is equal to K Ca Cb. Okay, so the feed is equal molar in A and B, and the entering concentration of A is 0.5 mole over decimeter cube. So this would be the Ca0. Alright, and A and B actually is equal molar, means that Ya0 is equals to Yb0. Okay. Okay, so the specific reaction rate is K is 4 decimeter cube over mole dot S. Write the rate of reaction negative RA solely as a function of conversion. Okay, so what you need to do is you need to have this term in terms of X. Okay, means that you have to expand the equation which involve there is a X in the function or in the equation. Okay, so take reactant A as the limiting reactant. Okay, so from here, what you need to do, you have to divide first the stoichiometric equation, and it becomes A plus B over 2 is equal to C. Alright, so automatically you will can calculate the del, which is equals to 1. Okay, 1 here, minus 1 over 2 for B, and minus 1 for A. Okay, so the value should be negative 0.5. Okay, so after you get this, automatically you can get the value of the epsilon, which is epsilon is equal to Ya0 del. Okay, so from here, Ya0 is equal molar means that this is 0.5, this is 0.5. Okay, so 0.5 times with the minus 0.5, the value should be 0.25. Okay, now you need to proceed with the stoichiometry table. Okay, so you have a species of A, sorry, I kena buat dalam ni. Okay, we have initial, we have change, and we have a living here. Okay, so we have a A, B, and C. So this definition would be FA0, FB0 equals to theta B FA0. Okay, this one I don't have to explain to you, but I dah repeat banyak kali benda ni. FC0 and theta C FA0. Okay, so the change, okay, due to the reaction occurs should be FA0 X. This one is minus 1 over 2 FA0 X, and this one is FA0 X. Okay, it should be positive here. So the value here, alright, for the A, okay, should be F A is equal to FA0 minus with the FA0 X, and we have FB here is equals to theta B FA0 minus with the FA0 X. Okay, or you can write down as FA0 theta B minus with the X. Okay, for FC it should be theta C FA0 plus with the, this one, sorry, ni ada half ni. Okay, this one I got half. Okay, and then this one plus with the FA0 X. Alright, so this one is 0. So we have FC is equal to FA naught X. Alright. So now what you need to do is you only need to expand the A and B only, because the question asks you to write the rate of fraction, which is negative RA is equal to KCA CB. Okay, so you have to convert this into concentration. Okay, so for the CA is equal to FA over V, and then we have FA naught 1 minus X, okay, over with the, remember this is variable volume, so V naught plus 1 plus epsilon X. Okay, so this one we will have CA naught 1 minus X over with the 1 plus epsilon X. Okay, you have the value of the CA naught, okay, which is 0.5 mole over this decimeter cube. Alright, and then X we don't have, just leave it there, and you replace the value, the epsilon with the value, which is minus 0.25. Okay. So you will have 0.5, okay, mole over decimeter cube times with 1 minus X, okay, 1 minus with 0.25 X. Okay, then you have a CB. Okay, so CB I terus translatekan dia lah sebab tak cukup ni, dia bersama juga macam A. You will have CA naught theta B minus with half X or with the 1 plus epsilon X. Okay. So you need to get what is theta B. Okay, remember theta B is equals to YB naught over YA naught. Okay, so this is equimolar, which is, this is 0.5 and this is 0.5. So the value will be equal to 1. Okay, so just masukkan, you will have 0.5, okay, mole over this decimeter cube. Okay, 1 minus 1 half here, and 1 minus 0.25x for the epsilon. Alright, so just masukkan balik lah, which is okay, masukkan balik, which is negative RA is equal to KCA CB, okay, is equals to, masukkan balik you, and then you simplify, you akan dapat 1 minus X. Okay, alamak, teruknya saya punya tulisan. Okay, so we will have 1 minus X, 1 minus half X, okay, over with the 1 minus 0.25 kuasa 2. Okay, you kena simplify kan, baru you boleh dapat kuasa 2 mana datangnya. Okay, so mole over decimeter cube second. Okay, tengok balik yang value ni lah, daripada mana you boleh dapat tahu sebenarnya daripada sini. Okay, sebab given K is in term of decimeter cube mole per second, and we have CACB dalam mole per liter, decimeter cube, and then mole decimeter cube. So you just tinggal ni. Okay, so at the end dia akan tinggal mole over decimeter cube second. Okay, so don't forget to write down the unit lah. Okay. So for exercise 4, okay, this you have to do it by your own self. Okay, I just want to to explain the C part. Okay, how to get the answer. Okay, so this one you just do the stochastic table. Okay, so this is the flow vector, which means it is in the flow system. Okay, and it is isothermal. Okay, and the pressure changes is negligible. Okay, means that there is no change of pressure. Okay, so a mixture of 90 mole per min of A and 135 mole per min of inert is fed into the reactor at 15 liter per minute. Okay, so this would be the, ingat kalau mole per minute should be F. Okay, so this is the FA naught and this is FI naught. Okay, and feed into 15 L per minute. Okay, so this is a volumetric flow rate. Okay, liter per minute. Okay, so you just construct the table in terms of the F. Okay, and for the concentration, make sure from the F that you obtain the leaving. Okay, for F A, F B, F C, you need to convert into concentration. Okay, so you can ada CA, CB, and CC. Alright. So the value for this one, okay, I just tulis je lah. You try to do by your own self, okay? Sebab kena juga buat sendiri exercise, because nanti you wouldn't know which part of yang you tak faham, okay? Alright. So for this one actually C part ni dia sebenarnya berkaitan dengan next chapter. So this one I reserve dululah. Okay, sebab dia nak dapat volume ni. Okay, so daripada volume tu macam mana nak dapat, you kena dapat dia dari design equation. That will I have to explain to you later on. Okay. So for this exercise part ni pun try to do it by your own self. Okay, tapi I akan bagi the value lah. Alright. Okay, sebelum tu saya bincang dulu. Okay, so a mixture of 45% SH4 and 65% oxygen. Okay, we can put it as a YA0 and also YB0 here. Okay, is charged to a constant volume. Okay, so this is constant volume, which is this one is equals to V here. Okay, so this is flow reactor. So flow reactor bukan V ni, itu adalah untuk batch. Okay, kalau flow dia kena volumetric flow rate. So volumetric ni adalah sama dengan volumetric of initial. Okay, constant volume flow reactor dia dah bagi tahu. So that's why you have to read word by word, alright, in the question, so that you can understand what kind of system is that. Is it a flow? Is it a batch? Is it a constant? Is it a variable? Okay, so this one you don't have to consider. V is equal to V naught 1 plus epsilon x. Okay, so this one tak ada. This is for variable. And it is given A plus 2B is equal to C plus 2D. Okay, so the reaction occurs at constant pressure of 1000 kPa. So this is the pressure, and constant temperature of 150 degrees Celsius. Okay, so this is a T. So it is given also the R. Okay, assume that the reaction is first order with respect to the both reactants. So means that negative RA is equal to KCACB. Okay, so based on the CH4, okay, this would be the limiting reactant. Okay, so you need to construct a stoichiometric table, okay, for the F system, for the flow system. Okay, so you just construct lah. Okay, then you need to get the what is CH4 in the function of X. Okay, this is the one that kita buat sebelum tu lah, exercise number 3. Okay, so you should have 0.128 okay, mole over decimeter cube. Okay, 1 minus X. Okay, so this should be the answer. Alright. Okay, this is in terms of concentration tau, bukan rate law. Should be CA. Okay, jangan salah. Okay, so for the then you need to have a concentration of O2, CO2 and H2O. Okay, so this is just a direct method aja. Okay, so the value of the CO2, okay, which is the CB, okay, you should have minus 0.046 mole over decimeter cube. Okay, and for CC, which is the carbon dioxide, the value is 0.1152 mole over decimeter cube. And for CD, which is the H2O, you should have 0.23 mole over decimeter cube. Okay, alright, so this would be the answer. Alright, so try to do the question for 6 pula. Okay, yang ni senang juga. This one is a product supported by iCare Manufacturing. Okay, so you just construct a graph, construct a stochastic table. Okay, so this one would be in a, what do you call it, flow system. Okay, itu sajalah, tak perlu nak tukarkan kepada concentration, sebab bila you tengok dekat sini tak ada pun tanya pasal concentration. Okay, so dah setakat awak dapatkan F tu pun dah cukup. Okay, untuk stochastic table. Okay, we move into the last part, which is material balance. Okay, so material balance is important for you in order to have a design equation. Okay, so the design equation you will use in the next chapter to get what is the volume of the reactor, as well as what is the space-time of the reaction. Okay, so you need to have a good knowledge in material balance, and the material balance for each of the types of reactor like batch, PFR and CSR will have a different equation. Okay, so let's say we have a general material balance. Okay, for example, we have a closed system here. Okay, it's a reactor, and there is a volume here. Okay, so there is a initial value, okay, initial flow ataupun concentration ke. Okay, and then there is a number of A here, alright, being react, and then NGA ni as a reaction lah occur, and then there is a effluent here ataupun outlet of FA. Okay, so let's say, okay, so the general mole balance on system volume V is denoted with in is minus out plus with the generation, which is this GA, is equal to accumulation. Okay, the accumulation of this one, right, the accumulation of number of moles. Okay, so we have a mole per second. Okay, remember F is in term of mole per second atau mole per time pun boleh, any of ni lah, unit second ke hour ke minute ke, minus with the FA plus FRA dV is equal to dNA over dt. Okay, so you have to have this general knowledge. Alright, it's just that you will change it according to the system or according to the type of the reactor. Okay, so let's say we have a batch. Okay, so if there is a batch system, okay, means that there is no in, there is no out. Okay, there is a generation and there is an accumulation occurs in the reactor. Okay, so we can cancel this one and cancel this one. Okay, we will have RAV equals to dNA over dt. Why we have V instead of R dV? Okay, because in a batch the volume is constant throughout the time. Okay, there is no change with the time, with the volume. Okay, so contohnya at T0, T1, T2, okay, the volume still sama. That's why we can put it as V only. So RAV is equal to here dNA over dt. Okay, so from here, okay, we have a minus here. Okay, in the direction. Okay, so from here you put it as at negative RAV ni, biarkan. Okay, it's just that you have to expand this NA. Okay, so what is NA? Back to the your fundamental knowledge of the chemical reaction, whereby we have a X is equal to number of moles reacted, okay, over with the number of mole feed. Okay, means that you rearrange this, you will get this equation. Okay, so you just plug in this one, NA0 minus NOx here, alright, and put ni differential memang ada, kena remain here. Okay, you just expand the NA here. Okay, so dNA0 we don't have, kita tak boleh differentiatekan at T0, sebab dia tak ada differentiate untuk apa. Yang macam ni dia boleh differentiate in term of X, yang ni tak ada. Okay, so we can cancel it 0 here. So what remain here is NA0X over dt. Okay, alright, so here actually we can put it, sebenarnya ada di sini. Okay, so rearrangekan dia jadi NA0 dx over dt. Okay, so you akan cancel here jadi positive here. Alright, so this is the question lah. So you have a RAV is equals to NA0 dx over dt. This is negative. Okay, so this is how you get lah the batch. Okay, so this is the one that I have explained before this. So we can cancel F and not minus FA for batch reactor has neither flow in nor flow out of reactor while the reaction is being carried out. Okay, that's why we don't have integration of dV. Okay, the dV, the volume does not change according to time. So operate as unsteady state. Accumulation is dNA over dt. Okay, kalau dia steady state baru kita boleh omit this one. Okay, make it as 0. So the reaction is perfectly mixed, then there's no variation in the rate of reaction throughout the reactor volume. Okay, this is the one I explained to you lah. And then we have a CSTR material balance where there is a in and there is a out. Okay, during the process. Okay, so from here, of course, from the diagram itself, it shows that there is a FA naught and there is a FA. Okay, so and then this one we can cancel as 0 because it works in a steady state. Okay, for continuous process. Okay, so we have this one. Okay, since it is a well mix, okay, same as like batch, kita assume as a homogeneous reaction ni. So you can have FRADV as a RAV, same like as batch, and this one you equal to 0. Okay, so what's remain is FA naught minus FA plus RAV is equal to 0. Okay, so you arrange it in order to get what is the volume. So V is equal to FA naught minus with the FA minus with the RA. Okay, so this one actually if you want to put into in terms of conversions, okay, you can expand this equation like FA naught is equal to what is FA. So remember FA is equal to FA naught 1 minus X. Okay, which means this one you can expand it as FA naught minus FA naught X over with the negative RA. Okay, so you cancel here, V is equals to FA naught X negative RA. Okay, alright. So this one you will be using it a lot in the next chapter. Okay, for the PFR material balance, okay, we have a cylindrical tube here, and there is at different axial, we call it, ataupun at different point of location, dia akan ada different reactions. Okay, so setiap kali volume kat sini, dia akan ada different reaction, and this one pun ada different reaction, RA3 and so on. Okay, so we have a FA0 and FA here. Alright, so this is considered as a steady state, work as a steady state sebab ada continuous mode. Okay, so you can cancel it to 0, and what left is FA0 minus FA plus integration of RA dV is equal to 0. Okay, so when you differentiate it, how you get this one? Okay, let me explain first why this one is not same as what they call it CSTR and batch. Okay, because FRADV, okay, is not equals to RAV. Okay, because it's not well mixed. Okay, that's why dekat different volume dia akan different RA. Alright. Okay, so how we get the DFA here over dV here actually is dividing, okay, by the changes of volume, and we arrange it. Okay, for example, we have a F, okay, A over V, F A for V plus the changes of V plus with the R A theta V, delta, I call it delta, ataupun I tak ingat nama simbol triangle is equal to 0. This is means that there is a changes. Okay, so daripada sini sebenarnya this is a FA0, okay, this is the FA, okay, and this is yang ni kita sebenarnya boleh tulis as a R V macam ni. Okay, so daripada situlah kita ada this one. Alright, boleh define the as dFA over dV is equals to RA. Okay, so sebenarnya dia ada limitation yang you belajar ni lah, macam mana you nak translatekan dia jadi equation macam bawah tu, macam ni lah. Alright, which is ingat tak? Tak tahu you ingat lagi dalam calculus, which is x plus theta x, alright, minus fx over with the change of x is equals to df over dx. Okay, so dalam bentuk ni sekarang x ni adalah v dia, in the function of v. Okay, that's why df ni adalah v. Okay, so f dia adalah in term of the flow rate. Okay, so flow rate dia akan berbeza with respect to the volume. Okay, so this is the volume necessary to reduce the entry molar flow rate from Fn0 to the exit molar flow rate of Fa. Okay, so tak apa, nanti you akan lebih faham untuk the next chapter. Okay, so this is the summary of the differential form, algebraic form and integral form. Okay, so you boleh ada this kind of form. Okay, it's just that for CSTR ada special case, dia hanya untuk algebraic form. You tak boleh letak ada integration ataupun differential. Okay, yang boleh hanya untuk batch and PFR. Okay, yang ni nanti akan terangkan for the integral form ni dalam topik number 4. Okay, so get ready everyone. So PBR ni tak payah, this one we will not cover for this fraction. Okay, so what does mean by design of equation? Design equation ni lah you akan belajar in topic number 4, whereby macam mana you want to get the volume, okay, as well as how to get the T here. Okay, for example macam ni lah, contoh kita nak dapat T. Sebenarnya I nak bagi secara simple je lah explanation, tapi bukan appropriate way. Okay, so Fa0 adalah bersamaan dengan Ca0 over V0. Okay, so kalau kita ada Ca0 over V0, okay, and kita boleh dapat V0 ni relate dengan V. Sebab apa? V is the volume. Okay, kita per dengan V0. This one is volumetric flow rate. Okay, this is in decimeter cube. And this one is a decimeter cube over second. So you akan dapat what is T. Okay, you akan dapat dalam second. Okay, faham tak? So ini akan apply to next topic. Okay, so that's all from me. Hope my explanation through this recording lecture will have a clear view and you could grasp what I've been explained, okay, throughout this session lah, recording session. Okay, see you for topic number 4. Thanks.